Hi, everyone. Thank you for coming. We are honored to have with us today Birgit Vogtenhuber. I apologize for probably mispronouncing the name. Birgit is from Graz in Austria, University of Graz, and she's a combinatorial and computational geometer. And I'm especially happy to have her here because when I was just a beginning graduate student, I used to rely on one of her papers all the time to kind of learn the state of the art of the field. So it's nice to have her in the seminar. And yeah, now I can be quiet and let's hear from Birgit.
Thank you very much. Now I'm curious. I'm going to have to ask you afterwards which paper that was. And let me share my screen. This one. Okay. Can you see my screen?
Yes.
So today I'm going to talk about generalized twisted drawing. Those are weird but very nice drawings with very nice properties. And the talk is based on a bunch of papers together with Alfredo and Javier from Universidad de Zaragoza. Alexandra from originally at TU Graz, she did her PhD with us, and Oswin Eichholzer also from TU Graz. And Alex is now in Fernuniversität in Hagen in Germany. So I'm going to start with a short outline, what I'm going to talk about. I'm going to introduce simple drawings of graphs. I'm going to introduce plane substructures in those drawings, and then I'm going to talk a whole lot about generalized twisted drawings. Those are not yet so famous. And then talk a little bit about why are they, one of the many reasons why are they interesting. So I find them interesting just by their properties and the things that one can learn about them, but they're also interesting for simple drawings in general. And then I'm going to conclude with a whole bunch of open questions with a very incomplete list of them on this topic. So what are simple drawings? First of all, what's the drawing of a graph? In a drawing of a graph, the vertices are distinct points and the edges are Jordan arcs, so non-crossing arcs between their vertices. And those edges shouldn't pass through other vertices. So that could be an edge in such a graph and with between two vertices, and that's a situation that is not allowed if this is one edge, it shouldn't pass through other vertices. With this definition, we still don't get very nice drawings of graphs, especially if we pick a bunch of points and then we pick an additional as vertices, and then we pick an additional point in the plane. We could decide to draw every edge through that point. And so this would be a drawing of K4 that I don't find very readable. And I'm probably not alone with that. Also, this drawing is guaranteed to not have larger plane substructures than a single edge, so that's a bit boring. So let's add another property that I find sounds very reasonable, and I'm not the only person. So we want that pairs of edges intersect at most in one point, and this point is either a common vertex or a proper crossing. And those drawings are known as simple drawings of graphs, or as simple topological graphs, or as good drawings, or as drawings, because this other thing isn't the drawing enough. And they have been quite widely studied. So in those drawings, any of those situations down there would be forbidden, like tangencies on the left side, or crossings between incident edges, or something weird like on the right side here. Okay, so that's what simple drawings are. That's what we're studying. One special case that is extremely well studied are straight line drawings. So those are drawings where the edges are straight line segments. Then they're especially simple because two straight line segments, if the vertices are in sufficiently general position, cross in a single point. And also the positions of the vertices determine the whole drawing. So one could also just call them point sets. And then simple drawings of the complete graphs can be seen as a generalization of point sets in general position. Now, where do these simple drawings live? Straight line drawings classically live in the plane. Simple drawings could also live, for example, on a sphere. They could also live in the plane. And I'm not going to go to any more complicated surface than the plane or the sphere. But for most of the things, I'm actually not going to care whether it's the plane or the sphere that these drawings are on. Now, there are infinitely many drawings, even if I take a single point, and that's a bit of boring again. So let's try to group drawings by similarities. We're going to consider two drawings as equal if they either, with some appropriate mapping of the vertices, have the same topology of the sphere. So on the sphere, so if we look at the plane graph that results from the planarization of the drawing, if those two plane graphs have the same combinatorics, including the same phase properties and everything, then they're strongly isomorphic. And a weaker way of isomorphism is to just require that the same pairs of edges cross. Those two drawings here are both strongly and weakly isomorphic. And let me remark that when we're looking at plane substructures or stuff like that, then actually weak isomorphism is enough. So any two drawings in the same weak isomorphism class have the same crossing edge pairs, so they have the same plane substructures. If we look at simple drawings of complete graphs, there are obviously two different straight line drawings of the complete graph on 4 vertices, but there are of course many more. However, these many more naturally group in two groups, the ones with a crossing and the other ones with a triangular convex hull and no crossing. And in each of those groups, all the drawings are strongly isomorphic, and the two groups amongst each other are not weakly isomorphic and not strongly isomorphic. We go for simple drawings. The situation can look a little more weird, but it's in the end not more complicated than this. So on the left side here, we have crossing instances of K4, and on the right side here, we have non-crossing instances of K4, and that's also the only difference that they have. This dashed line here would say if we wanted to distinguish on the sphere also the outer face as a special face, then we would have this additional splitting, but for this talk, we're essentially not going to care about that. Now, if we go for K5, then there are 5 different drawings, and I'm going to give them names. The G ones are geometric drawings, or can be realized as geometric drawings, as straight line drawings of the K5 with 1, 3, or 5 crossings. And then there are 2 more that one can't draw with straight lines. The T5, that is also called twisted drawing, and the T3. T5 has 5 crossings, and the T3 has 3 crossings. T5 has another very interesting property. It has an edge that is as much crossed as possible, meaning that it is crossed by all edges that are not incident to any of its endpoints. And if we go for simple drawings of Kn, because every subdrawing that is an induced subdrawing on 5 vertices is a drawing of a K5, then these subdrawings are going to be all one of those. Now, in order to compute with simple drawings, a very nice abstraction are rotation systems. So the rotation system of a simple drawing is a very simple thing in the end. It just records for every vertex the cyclic order of the emanating edges. For some arbitrary labeling of the vertices, we don't care which, because we don't care about labels here in this talk. And then if we do that for all vertices, that gives us the rotation system. And it has been shown that for complete graphs, the rotation system actually determines completely which edge pairs cross. And also the crossing edge pairs determine the rotation systems. So that's an equivalence that has been stated and shown by Joan and also by Jan Künschel, but the proof by Joan has only been published far after the proof by Künschel. That's why both names are here. So that implies that whenever we have two simple drawings that are weakly isomorphic. Recall those were the ones with the same crossing edge pairs. Then they also have the same rotation system for some labeling. And it also means that plane substructures only depend on the rotation system, so we can compute from the rotation system very easily which edge pairs cross. Then there are also abstract rotation systems. That's just some cyclic order of, for every vertex, some cyclic order of the remaining labels. And a very interesting result in that direction is that such an arbitrary abstract rotation system is realizable as a simple drawing if and only if every 5 tuple is realizable. So in contrast to abstract order types, a classic abstraction for point sets, where it is hard, like existential of the reals, hard to decide whether an abstract order type is realizable. Here we get a polynomial time algorithm that is very simple. Okay, so let's come to plane substructures. So if we want to look at plane substructures of complete graphs and of simple drawings, and we want to know a whole lot about them. But let me start with the I find easier case of straight line drawings. If we have a straight line drawing of a complete graph, then the structure of any maximal plane subgraph is very well known. This is called a triangulation. It's a two-connected graph. And the number of edges in such a maximal plane subgraph is 3n minus h minus 3, where h is the number of points on the boundary of the convex hull. And then naturally, every simple drawing of the complete graph contains a plane perfect matching, or n half pairwise disjoint edges, and half rounded down, because if we have an odd number of points, one is left over. One way to see this is just to connect the first with the second, the third with the fourth, the fifth with the sixth, and so on, point in increasing x order. I think that's what I did here. And also it's well known that simple drawings, straight line drawings of complete graphs always contain plane Hamiltonian paths, like for example, again, connecting the points in x order, and also plane Hamiltonian cycles. One way to do this would be to look at the edge between the first and the last point in x order, and then have two paths, one on the top and one on the bottom. Last point on substructures that I'd like to look at here for the moment are empty triangles. So what's an empty triangle? It's a triangle that is spanned by 3 points and doesn't contain a point in its interior. In straight line drawings, it's very easy to see that whenever we take an arbitrary edge of the drawing, of which we have n squared many, then the point that is closest to the edge is going to form an empty triangle with the edge. And as an upper bound on the number of empty triangles, we get n choose 3, because every triangle could be empty. Okay, so that was the easy part. That were straight line drawings. So let's go to simple drawings. And I'm depicting here one of those examples of a K5. If we look at the structure of a maximal plane subgraph and the number of edges in there, then one example maximal plane subgraph could be this blue set of edges here. And alternatively, I could also take this blue set of edges. So I've now replaced two edges with a single one, but I can't add any further edge. So this means that the number of edges in a maximal plane subgraph actually depends on the choice of the subgraph, which is very different from straight line drawings. And also the structure of a maximal plane subgraph is not so clear. So especially it's not a triangulation, whatever triangulation means. But like in this example here, we have two non-triangle faces, so that's surely not a triangulation. But what we know by now is that it's a two-connected graph. So both these bounds here for the number of edges and the fact that it's a two-connected graph are a result of Alfredo, Javier, and Alexander. And they also showed that deciding whether a simple drawing of a complete graph contains a plane subgraph with k edges is NP hard. one of the very few results of hardness on complete graphs. Okay, so that's quite different from simple drawings. Now, if we from straight line drawings, now if we look at disjoint edges and long plane paths and cycles, in this example here, I have a nice Hamiltonian cycle and hence also a Hamiltonian path, and hence also n half rounded down pairwise disjoint edges. So at least this example is not a counterexample to this, and still open whether this is always the case or not always. If we look at the number of empty triangles, then this example here maybe is not a so good one. So let me take a different one, yet another simple drawing of a complete graph. Just to recall, a triangle in a simple drawing of a complete graph is simply the closed curve that is formed by three vertices and their incident edges. This is a simple closed curve because no pairwise incident edges are allowed to cross. So this object splits the plane or the sphere into two parts, the plane in an outside and an inside, and the sphere into, if you want, so equal parts. Here's another triangle in this drawing, and both of those triangles are non-empty because they contain a point on the interior and a point in the exterior. And in simple drawings, we tend to call triangles empty if one of the sides of the triangle does contain all the points, the remaining ones, and the other side contains none of the remaining points. So in this drawing, this here would be an empty triangle. This would be another empty triangle. So that one is, if you look at it at the plane, in the plane, exterior empty. And very much in contrast to straight line drawings, it is not true that every edge of a simple drawing is incident to an empty triangle. Especially in this drawing that I've shown here, this can be generalized. There are only 2 and -4 empty triangles, which implies that most edges are not incident to any empty triangle. As a lower bound that we know by now, there are at least n empty triangles, and that comes from the fact that one can show that every vertex is incident to 2 empty triangles, and if it's only 2, then it's a special vertex. Okay, so I'd like to talk about these 3 structures, so pairwise disjoint edges and plane paths and cycles and empty triangles a little more later. But before I go there, I should introduce generalized twisted drawings first. I promise that this talk is about them. So let me start with a more general definition because we're going to need the second side as well later. A simple drawing is called C-monotone, short for circulary monotone, if there exists a point in the plane such that any ray that emanates from that point intersects every edge of the drawing at most once. So those 2 here are instances of C-monotone drawings. If we look at an edge, then any ray that emanates from O intersects it at most once. We could also draw this edge like this, would still be fine. What would not be allowed is something like this, because then we have rays that intersect the edge more than once. And then there are 2 special cases of C-monotone drawings. The one that is depicted to the right, we call it a monotone drawing, and the reason is that there exists some ray that emanates from O that doesn't intersect any of the edges. So we could actually open up the drawing so that we have the vertices on a straight line and the edges twiggling around them, the edges being X monotone curves. And the one on the left is an instance of our generalized twisted drawings. Those have the property that there exists some ray that intersects every edge of the drawing. So somewhat the contrary of monotone drawings. Why the name generalized twisted? Well, this comes from so-called twisted drawings. I've mentioned it before. So a twisted drawing of a complete graph is one where there is a labeling of the vertices such that the edge VIVJ crosses the edge VKVL if and only if I, K, L, and J are in this order. So we first have, so they're not interleaving and have this special order. These drawings have been introduced by Harbert and Mengerson for many reasons. Harbert showed that they only contain 2n-4 empty triangles, and they've been named twisted drawings by Bach, Solimoschi, and Todd. So this property, if we look at this, we look at an edge in this drawing. So every edge here is a polygonal chain. That's also fine. Then it would be intersected by exactly these three edges because these three edges fulfill this special intersection property. Now, twisted drawings can be shown, and that's relatively straightforward, to also be generalized twisted. So here we would have a ray, and that drawing maybe is not completely C-monotone, but nearly. So every twisted drawing is strongly isomorphic to a generalized twisted drawing, but the converse is not true. Generalized twisted drawings are a larger class, so there are more generalized twisted drawings. For n equals 6, there are 3 of them. Why are twisted drawings interesting? Well, they are interesting because they have interesting properties. One property by definition is that they admit a curve that crosses every edge of the drawing exactly once. This ray OZ would be such a curve. And an open question that I'll answer in this talk is which simple drawings of the complete graph admit such a curve. Another property is that by this crossing property of this curve, of this ray from O to Z, every triangle is crossed exactly 3 times. So every edge of the triangle is crossed exactly once. And hence, O sits in the interior of this triangle, and the second point Z that I've marked here on the other side of the drawing of the ray sits on the outside of this triangle. And that's true for every simple triangle in the drawing. Something that immediately follows also from the curve that crosses every edge and from this empty triangle property, or this triangle property, is that there exists a pair of cells such that the one cell lies in the interior of every triangle and the other cell lies in the exterior of every triangle, or those cells are on opposite sides of every triangle. And also something that is obvious by definition, if we take an induced subdrawing, so we remove some vertices and their incident edges, then we still are C-monotone, we still cross every of the remaining edges, so every induced subdrawing is also generalized twisted. One more property that I've marked here already in this drawing is that these antipodal cells that we find here are actually not only arbitrary cells, but they are cells that contain at least one vertex on their boundary. Now, I've talked about rotation systems before, so let me talk about them again. If we have a rotation system, we don't have a drawing, and especially we don't have C-monotone curves. So we call a rotation system of the complete graph generalized twisted if there exists some drawing of that rotation system that fulfills the properties of being generalized twisted. And hence, a drawing with a generalized twisted rotation system is weakly isomorphic to some proper generalized twisted drawing. If we look at generalized twisted drawings for small cardinalities of n for few vertices, then for n equal 4, there is exactly 1. That's the crossing K4. And here would be 2 examples of antipodal cells and curves for those cells. So we see that essentially the drawing is very symmetric. It's going to be 2 opposite triangular cells of the K4. For n equal 5, there is also exactly 1 generalized twisted drawing, and that's the twisted K5, the T5. Also, this one admits more than one curve. So here is one, here is another one, and this time the cells where these curves start and end are not looking the same as in the K4. So as for n equal 5, we have only one unique drawing that is generalized twisted. And as every subdrawing of a generalized twisted drawing is generalized twisted, we know that if we have an at least 5, then every 5 tuple, every induced K5 has to form a T5 in the rotation system. For n equals 6, we had 3 different rotation systems that fulfill the properties of being generalized twisted. We saw the pictures before. And there is one more rotation system that has only twisted drawings of K5 as subdrawings. Here's a drawing of this one. And this drawing has these 2 blue marked cells. I'll not have you check this, but these 2 blue marked cells are actually antipodal cells. So for every triangle in this drawing, this one cell is on the one side and the other cell is on the other side. However, these cells do not have vertices on their boundary. And if I make a different drawing that is weakly isomorphic to the one before, then in this different drawing, we don't find any such cell pair. Now, we expected that starting from n equals 7, 8, and so on, we would find more generalized, more rotation systems that only have T5s, but are not generalized twisted. However, for n equals 7, it turned out that checking all the rotation systems of 7 vertices, that we could have all the ones that have only T5s are actually generalized twisted, which raised the question under which conditions rotation systems that only have T5s, that's an obvious necessary condition, are generalized twisted for larger n. And this is a question that I plan to answer in this talk as well. Before that, I'd like to come to some twisted generalizations. So if we look at a simple drawing of the complete graph, and this simple drawing is weakly isomorphic to a generalized twisted drawing, then one can show that it actually contains an antipodal VI cell pair. On the way to here, we need to show that this means that antipodal cells then are cells that have vertices. And then if they contain an antipodal VI cell pair, so an antipodal cell pair with vertices on the boundary of each of these cells, then we can show that it also admits a curve that crosses every edge exactly once. And if we have such a curve, then we can use this curve to extend the drawing by 2 additional vertices, the endpoints of that curve, and edges incident to those new vertices, such that the drawing together with these new vertices and the edges to all the other vertices is a simple drawing of the complete graph on n plus 2 vertices. The edge OZ crosses every edge of D, and no edge incident to one of those 2 additional vertices crosses each other. So those 2 together with the other vertices induce a plane K2n. And then with this property of the plane K2n, we could show that actually D is strongly isomorphic to a generalized twisted drawing by using a property. So it was known that such a drawing that contains such a plane K2n, then the remaining vertices, the n vertices, form a C-monotone drawing or are weakly isomorphic to a C-monotone drawing. And we could also show that they're actually strongly isomorphic to a C-monotone drawing in this case, which gives that we have this drawing that we started with as being weakly isomorphic to a generalized twisted drawing, ending up as being strongly isomorphic to a generalized twisted drawing, which closes the cycle and says that all these properties are actually equivalent. So this is a whole bunch of very combinatorial characterizations of generalized twisted drawings that actually only depend on the rotation system, and the last one also depends on the drawing. And we found this very nice and very interesting. So I'm still excited about those drawings for this reason. But now let me come back to the 5 tuples. And what we observed is that for n equals 7, every rotation system that has only T5s is generalized twisted. And surprisingly, this property holds also for any n that is larger than 7. So note it does not hold for n equals 6. There we had this counterexample. And to prove this property for general n, we used induction, and we used as an induction base the space from 7 or from 7 to 10, which we verified by computer, because for the very last step of the induction step, we need a sufficiently large drawing to start off with. And then in the induction step for n equal 10, we looked at a drawing of Kn for which every induced subdrawing has a generalized twisted rotation systems, and showed that then also the rotation system of the generalized twisted drawing as a whole, is generalized twisted. Sorry. So how did we do that? I'm not going to go into any details of the proof. It's quite lengthy, but I'd at least like to sketch some ideas of this induction step. So the main proof ingredients that we're using are, of course, properties of generalized twisted drawings, empty triangles in them, and especially empty star triangles, properties of maximally crossed edges in simple and generalized twisted drawings, and these antipodal VI cell pairs, properties of them, and an estimate on how many of those pairs we could have. And then for the induction step, a lot of small induced subdrawings of our drawing that we want to show something for. So let me quickly sketch what are star triangles and empty star triangles. So a triangle in a simple drawing with vertices x, y, z is a star triangle at a vertex x if the edge yz is not crossed by any edges that are incident to x. So in this example down here, this blue triangle is a star triangle at x because the edge yz is not crossed, but also this triangle is a star triangle at z because yx is not crossed, and it's not a star triangle at y because the edge xz is crossed by an edge incident to y. If we, there is an edge too many. If we add this edge from z going out through the edge xy, then this triangle is not star at z anymore. And if we add this edge plus the vertex incident to x, then this triangle is not a star triangle at any of its 3 vertices. So triangles don't have to be star triangles at any of their vertices. And this triangle meaning here the interior of the triangle. And also the exterior, because the crossing properties are the same. So if I look at the boundary of the triangle, no matter whether I look at the inside or the outside, the crossing properties are the same. This would be an example of a triangle that is a star triangle at all 3 vertices. Now, why are star triangles interesting? If we take an arbitrary simple drawing of the complete graph, then Andres Ruiz Vargas and Rado Fulek showed that every vertex is incident to at least 2 empty star triangles, and the empty sides of these empty star triangles are interior disjoint. So they might share an edge, they surely share the vertex, but they don't overlap in their interiors. Moreover, if we look at the edges at the star vertex, then on the empty side of the triangle, they are adjacent in the rotation about that vertex. And these two things were an essential ingredient for first showing 2 1/3 empty triangles in simple drawings, and then later with additional properties in empty triangles in simple drawings. Now, if we look at star triangles in generalized twisted drawings are simple drawings, so we have at least 2 empty star triangles at every vertex. But actually, we don't have at least 2, but we have exactly 2 such triangles. So why is this? Recall that we have these two endpoints of our ray, O and Z, and they have to lie on opposite sides for every single triangle, so also for every empty triangle. So if, for example, O lies in the triangle XYZ, then it does not lie in the triangle, lies inside that one, and it lies outside the other star triangle, because those things are interior disjoint. And hence, the second triangle needs to contain our other endpoint of our curve Z. But then if we had a third triangle, we don't have a third endpoint of our curve crossing every edge. So this other triangle, which would be interior disjoint to the other two, can't exist in a generalized twisted drawing. So 2 empty star triangles at every vertex. One contains O and the other contains C. Further, if we look at the cell that contains our curve endpoint O, then this cell can be shown to have very special properties, especially if we look at an incident vertex of that cell, like VO here, then the triangle spanned by the 2 incident edges of VO that bound the cell and the third edge that connects those those two destination vertices clearly is a star triangle at VO, but in addition, it's an empty triangle. So no vertex lies in the interior of that triangle, not only in the interior of that cell. No cell can contain a vertex in the interior, but also not in the interior of the whole triangle. Further, this triangle is a star triangle at one of the 2 other vertices, and at the third vertex, all the edges emanate to the inside of the triangle. So they're on the outside, the 2 edges are adjacent, and on the inside, all the edges from this vertex U, in this case here, emanate, and they cross through the edge VOW. If we look at an arbitrary empty triangle, if this triangle has O on the empty side, then because it has the cell CO on the empty side, it also must have VO as a vertex. Otherwise, it would contain VO in the interior, which it must not as an empty triangle. So for every empty triangle, every vertex that is incident to the cell containing O is a vertex of this triangle. So in this example here, we would actually have 2 such vertices, but in the general picture on the right, let me stick with, it might also be only 1. Further, this empty star triangle is a star triangle. This empty triangle is a star triangle at either X or Y. And also, so one of the 2 points that are different from VO, and it is also a star triangle. It might also be a star triangle at both vertices. If this is the case, then at the third vertex, again, all the edges have to emanate into the interior of the triangle and then cross through the triangle because the triangle is empty. So this second vertex might also be VO instead of X. So this gives us a very special situation for empty triangles. And this is one of the main ingredients for proving that all rotation systems with only T5 and at least 7 vertices are actually generalized twisted. The second ingredient are maximally crossed edges. So any simple drawing of the complete graph contains at most one maximally crossed edges. For n equal 5, we can do this brute force by saying, well, there is only one out of those 5 different rotation systems that gives us a maximally crossed edge, the T5. And if we have a larger drawing and we assume that we would have 2 edges that are maximally crossed, then these 2 edges span 4 or 3 vertices. And in any case, we could add any 2 vertices in this drawing and obtain a K5 that has 2 maximally crossed edges, which is a contradiction. So why is that? Because if I have a maximally crossed edge, then that means that all other edges that are not incident to my vertex need to cross it. And that must hold true for every subdrawing as well. Now, if a simple drawing contains a maximally crossed edge, then one can show that this drawing has 2 antipodal VI cell pairs and hence is generalized twisted by the characterization from before. And moreover, these 2 antipodal VI cell pairs are incident to this maximally crossed edge and each on opposite sides of this edge. So each pair is on opposite sides of this edge. Like the blue is here is one pair and the purplish here is one pair. And so, yeah, I said that. So this edge, also this edge has 2 adjacent empty star triangles because we said that the cell that contains that is an antipodal, that is in an antipodal VI cell pair, then the triangle that is spanned by the vertices, the vertex incident to that cell is an empty triangle. So this triangle here completes to an empty triangle. Okay, so that were simple drawings that have a maximally crossed edge. Now, if we look at generalized twisted drawings and assume that a generalized twisted drawing has at least 2 antipodal VI cell pairs, then we can show that some vertex of these cells has 2 adjacent empty star triangles. And to do so, we use a lot these empty triangle properties and the fact that if we have the right situation here where the 2 star triangles of the vertex are non-adjacent, then V prime must be that middle vertex of the twisted drawing. And then we use a whole lot of properties of these antipodal VI cell pairs. So because Dn has this one vertex that has adjacent empty star triangles by the properties of before, the edge V1, V2 is incident to a maximally is incident to both cells. This edge is maximally crossed. And also it's incident to 2 antipodal VI cell pairs. And for that, we essentially only need drawings of K5 and seeing that if we have 2 antipodal VI cell pairs, then we find an edge that has to be maximally crossed. And for every additional vertex, so in every T5, and then for every additional edge for completing this to a generalized twisted drawing now needs to cross through this edge. Also, along the way of that proof, what we got is that any generalized twisted drawing has at most 2 antipodal VI cell pairs. So more than 2 cannot be. So we have either only one possibility of a cell pair to place O and Z, or we have 2 possibilities, but not more than this. So that gives us a lot of nice additional structure if we have a maximally crossed edge. And with this now we can complete the proof of our induction step. So now we have all the ingredients, and then the simple case is if we have some vertex that has two empty star triangles that are adjacent at one edge, then by the arguments before, we know that the star triangle vertices plus any x and y form a generalized twisted K6 with a maximally crossed edge. So hence also the whole drawing Dn contains a maximally crossed edge and is generalized twisted. The second version of the proof, or the second case of the proof, if every vertex of the drawing has two non-adjacent empty star triangles, recall that every vertex has two empty star triangles, but if they're non-adjacent for every single vertex of the drawing, then the star triangle vertex of an arbitrary vertex, that's, we call it V here, form a K5 because a T5 because we already have 5 vertices. And then what we look at is the structure of the whole drawing Dn inside such a triangle. So in T5, our vertex, our curve endpoint O would sit inside that triangle and C would sit inside the other. If we look at the whole drawing Dn, then it turns out by the fact that we have a generalized twisted drawing for every subdrawing of Dn inside this triangle, we must get some kind of grid structure of edges that come from V2 and from V1. And they can't come from V because this triangle is an empty star triangle V. And so this triangle needs to contain a grid cell with O for every subdrawing of this Dn. And then, so this could be for one. And then what we need to show is that in these cells of the subdrawings, so if I take a cell in a subdrawing, it can be larger than in the whole drawing, but not smaller. And then what we show is that the intersection of all those subdrawing cells still contains a grid cell. So placing the point O, the curve endpoint O in there then gives us the desired properties and symmetrically for the point Z. Then by the characterization that if we have an O and a Z that are antipodal, the drawing is generalized twisted, or the rotation system is generalized twisted. And for this step, we do need n to be at least 10 because we need a certain number of grid lines in these cells to guarantee that we find one cell in the whole drawing. Okay, so this finishes the characterization and implies that an abstract rotation system is generalized twisted if and only if every subrotation system induced by 5 vertices forms a T5 and gives us an ON to the 5 checking algorithm. Two open questions in this direction would be whether it is possible to determine in less than O of n to the 5 time whether an abstract rotation system of the complete graph is realizable as a simple drawing, or also whether a rotation system of which we already know that it's realizable as a simple drawing is generalized twisted. For the first question here, I don't have an answer. For the second question, I have, but I won't manage it in this talk, definitely. So there exists an algorithm that runs in n squared time if we already know that the rotation system is generalized twisted and it uses yet is simple and it uses yet another characterization of generalized twisted drawings. Now, very quickly, empty triangles in simple drawings of the Kn. So for that, we have essentially all ingredients from the observations before. The big question is how many empty triangles does a simple drawing of the complete graph contain? An obvious upper bound is n to the 3. If we take the points in convex position and a straight line drawing, every triangle is empty. As for lower bounds, I already said straight line drawings always have at least order of n squared many empty triangles. That's the currently latest bound. And the upper bound for the minimum is also n squared due to Imre Barani and Pavle Walter from 2004. For simple drawings, the best lower bound is linear, and it's exactly n up to now, and the best upper bound is 2n minus 4 by Harbord and his drawings. Now, we wondered whether we can say something about the number of empty triangles in generalized twisted drawings. And especially, we wondered whether we can prove this conjecture for generalized twisted drawings, at least if we already can't prove it for all simple drawings of complete graphs. And then when we started looking at generalized twisted drawings, recall we have exactly 2 empty star triangles at every vertex. One contains O, one contains Z, and every empty triangle is a star triangle at least one of its vertices. So those two things already together imply that we have at most 2 n triangles in total in any generalized twisted drawing of the complete graph. And then we could actually not only show that they contain at least 2n minus 4 empty triangles, but we could show that they contain exactly 2n minus 4 empty triangles. And with all the stuff from before, this only needs 2 ingredients that are left. One is that no empty triangle can be a star triangle at all 3 vertices. Why is this? If we have a triangle, it's an empty star triangle at all 3 vertices, then any induced K4 with these 3 vertices is a non-crossing K4, and that doesn't exist in a generalized twisted drawing. And then we could show that exactly 2 empty triangles that contain O on the empty side are a star at 2 vertices, and the same for Z. That then gives the -4 factor, or and one of those triangles we've seen, it's the triangle that bounds the cell containing O at the incident vertex, and then showing that there is exactly 1 second one always is a bit of case distinction and a lot of using properties of generalized twisted drawings again. So that finishes the generalized twist, the empty triangles. And now let me come. Should I still continue? It's already quite late.
Depends for how long, I guess. You can have a few more minutes, but
Then
maybe
let me
2
have
hours
like
would be too much.
no, I don't think I'll need much more than 5-6 more minutes, something like that.
Okay, sure.
So the last part that I promised in my abstract are plane substructures in simple drawings, and especially conjectures on Hamiltonian cycles and Hamiltonian paths. So it's conjectured that every simple drawing contains a plane Hamiltonian cycle. That was already conjectured by Rafla 1998. This conjecture is true if n is at most 9 by brute forcing the rotation system database that we have in Graz. And that implies that also the conjecture for the plane Hamiltonian path and for the n half disjoint edges is true for n at most 9. So all the upper bounds that we have for simple drawings of Kn due to these conjectures are n half disjoint edges, the length of a plane path being n minus 1 always, and or at most, and the length of a plane cycle being n at most. However, the lower bounds that we currently know are pretty far from that. So here's a short bibliography on lower bounds. for disjoint edges, we start with log n to the 1/6. At some point, break the log n in 2009, then have a huge step to third root of n, then to root n minus epsilon, or n to the 1/2 minus epsilon, and then to n to the 1/2. That's, to the best of my knowledge, the currently best bound. And for plane paths, the bounds are even lower, where the very last bound of n to the 1 divided by 9 is in an archive paper by Andrew Suk in the first version, but not in the second version of the archive paper. So I haven't managed to ask for the status of this one yet. What I'd like to very simply shortly sketch are those two, where the second here also holds for cycles and not only for paths. And because those are the ones that we proved using generalized twisted drawings. So our twisted results for plane substructures are plane cycles of length log n divided by log n for any simple drawing of Kn, and omega of n½ disjoint edges for any such simple drawing. And the main proof ingredients are, of course, generalized twisted drawings, and then monotone drawings that I mentioned in the beginning, and diary trees plus stars on the one hand, and plane matchings for the matchings on the other hand. So the only really unknown structure here are generalized twisted drawings. So let me start with them again. If we have a generalized twisted drawing of the complete graph, then we can show that it contains a plane Hamiltonian path, and if n is odd, also a plane Hamiltonian cycle. The main proof ingredient here is that for generalized twisted drawings, we know that if we have edges of alternating indices, so like these two drawings here, then those edges cannot cross as they are drawn here. So they're drawn crossing here, but this crossing cannot exist because in each of those cases, no matter how we try to complete the drawing, we're not going to be able to complete it to a generalized twisted drawing where every edge crosses the red ray. And then by this property, we can say whenever we have edges that would cross in the convex geometric drawing, then those edges are pairwise non-crossing in a generalized twisted drawing with the same vertex order. So this star here that can be completed to a full star gives us a path for odd n and also a cycle. And for even n, we get a crossing family of that type, so pairwise crossing edges that form a path. And here the closing doesn't cross the rest, so we can't say anything about the cycle by this simple argument. And that would be the drawing for Kn. And then using this property that generalized twisted drawings contain all these structure, we can show something for simple drawings by saying that every simple drawing contains either a monotone drawing of a KD for some D, or a plane spanning tree, spanning star plus a diary tree that is planed together for the same D. And then the monotone drawing contains a K square root of D that is either generalized twisted or monotone. And for those, we know the plane cycles. And also for the plane spanning tree plus the star plus the diary tree, it's easy to find a plane cycle, but of that other length. So that we already have. That is a well-known property. For showing this implication, so every circularly monotone drawing contains one of those, we can use Dilworth's theorem by doing a partial order on the vertices and saying we relate two vertices if I is smaller than j in this partial order and the edge crosses the ray, and otherwise, or if they're the same, and otherwise we don't relate them. And then if we take a chain or an anti-chain of the same size, then the chain gives us a generalized twisted drawing, and the anti-chain gives us a monotone drawing, and setting s equal t, we get the square root of n. So that's this part. And then for that part, we use a result that I've mentioned before by Alexandra and Javi and Alfredo on subdrawings of simple drawings. So what they showed is that any maximal plane subgraph, and now it's important that it's maximal, is biconnected, and then taking this, starting with the star and adding edges until we have a maximal plane subgraph, we obtain a plane drawing that contains the tree, the plane spanning star plus a tree. Now, if the tree has a vertex, has vertices only of degree smaller or equal to d, we have this d-ary tree. This has height at least log d, and hence we get our log d bound. And if we have a vertex with degree at least d plus 1, then we get a k2n or 2d in this form, and this k2d in this form gives us a C monotone drawing on D by Rado and Andres Resuagas. That's this part, and then that implies already all of this. And putting things together, choosing the right D, we obtain the bound of log n divided by log n. So let me skip. So that's for cycles and paths. Let me skip the disjoint edges and come to the conclusion. Generalized twisted drawings have a lot of nice properties. There are a lot of conjectures that are still open on simple drawings. There are a lot of questions also open for generalized twisted drawings. And I thank you very much for your attention.